So, hello everyone, welcome back. Now let us start problem number 5.12 on page number 229 of Griffiths electrodynamics. And he's saying that use the result of example 5.6, and which was that you need to calculate the magnetic field at the axial point of a uh, ring. And now he's saying to calculate the magnetic field at the center of uniformly charged spherical shell. This is very important. Spherical shell of radius r total charge, and it is spinning at angular velocity omega. So first of all, we need to consider a spherical spherical shell. A spherical shell means it is hollow from inside. All right, the charge or the current is distributed. The current is distributed only at the surface of the spherical shell. So simple, what we can do is if all the things are on the surface, we can consider a small strip like this on this spherical uh, shell, and such that uh, it is at a distance. You can say that uh, this is actually r na. This is at the surface actually of the spherical shell. So this is r, and so if this is r and this is theta, this is r cos theta, and what is this? This is r sin theta, simply from trigonometry. Now, what we need to do is we need to calculate the magnetic field by using the result. So we know that from that result it was mu naught. Sorry. First of all, I'll write the result only. It was mu naught I upon 2, and I think it was r square by r square plus z square raised to power 3 by 2. It was something like this. Yeah. So we need to calculate magnetic field over on at the center of, so from the center, from this distance, when you calculate the magnetic field, and it is spinning at a angular velocity omega. So suppose this is the angle and it is spinning about this axis with angular velocity omega. So what we'll do is, as we know that uh, the current current on this strip is will vary with respect to length. Why? Because on every point the length is changing. That's why how the current will change. Di is equal to k dl, where this is the current density k. All right. And we very well know that current density can also be written in terms of surface charge density, which is sigma v. You can read the previous pages of Griffiths electrodynamics. I guess it is page number, given on page number 228 or something like that. So we'll just substitute these values here, sigma into v into dl, and we very well know that, sorry, dl. What is dl? Dl is the length. So which is r, this r, and this d theta, this theta. All right. Suppose this is the strip of, we'll consider small angle. So the length element is r d theta only. So sigma, the charge density is q upon 4 pi. Sorry, sigma is the charge density. Charge density is q upon the ds. Sigma is d sigma. We will know the dq upon ds. So this is the surface area of the spherical shell is 4 pi r square, and v, as omega is given in the question, so we'll relate it with omega. V is omega r, and the other thing is r d theta. All right, di. So this becomes di. So now di becomes as q omega d theta upon 4 pi. And the most important thing here is the mistake I also did here, that what is this r. I should write it this r as r dash, because v is omega r, but that r is the perpendicular length. So the perpendicular length is r sine theta here. So I'll write as r sine theta. So one theta, sine theta will appear over here, due to that the distance from the distance is different. That's why that is not only r, that is r sine theta. So we'll just substitute these values in the dB equation, which is mu naught di upon 2 into r square. And what is r? Sorry, I should also replace it with this. R is here, r sine theta. I hope you remember from the ring thing that there was a circular ring, and this was given as r cos, this was as r sine. That's why the I think if you have seen my previous videos, you'll recall why I'm writing it as r sine theta and that r cos theta. Or you can briefly review the example number 5.6. If you face any difficulty in understanding that example, let me know in the comment section. I'll help you out. So again, r sine theta, r square sine square theta plus r square cos square theta. And the z thing, this was z, this was r, and so it was r cos, this was r sine simply, and this was r, I think this was r cos. You can just check it. All right, if this is theta, then simply this is r cos and this is r sine. All right, and this is whole raised to power 3 by 2. So we'll only the thing which is left is we need to integrate the by just putting the values q omega by 8 pi. I guess the 8 pi will become due to this 4 pi, this 4 pi and this to 8 pi, r square sine square theta upon r cube, and sine square theta plus cos square theta is 1, so it will get cancelled. So what things are left here? One sine theta will also come due to this. So sorry, sine theta and d theta. All right. Now we'll just integrate mu naught q omega 8 pi r integration sine theta sine cube theta d theta. And for a spherical shell, we very well know that theta varies only for this 0 to pi, and the mm, phi, the phi angle varies with 0 to 2 pi. I think you know that this is really common. All right, now magnetic field becomes as mu naught q omega 8 pi r into, so sine cube theta we need to relate now. So we very well know that what is sine theta. Oh, sine 3 theta. Sine 3 theta is 3 sine theta minus 4 sine cube theta. So we need sine cube theta, we'll just replace it here. So it is 3 sine theta minus sine cube theta upon 4. It is equal to sine cube theta. I think it is correct, I guess. Yeah. So what we'll do is we'll just plug in these values here, 0 to pi, 3 sine theta minus sine 3 theta, oh, sorry, upon 4 d theta, which becomes as mu naught q omega 8 pi r into, so sine the integration is cos minus cos and 0 to pi, which becomes as, so we'll see. All right, 3 cos minus cos 3 upon 4 into upon 4 into 3, sorry, upon 3 and 0 to pi. So on further simplification, we get mu naught q upon 8 pi r into, what is cos cos pi, it is minus 1, and cos it is also Again, it was 1, that's why minus 1 minus. Cos 3 pi 8 is minus 1. And what is cos? It is again minus 1. Minus of minus, minus 1. So, oh, and with 3 here. So we get 3 by 4 into minus 2 plus 2 by 3. I think that's correct. So it becomes as minus 4 by 3 into, 2, 6 minus 4 by 3, yes, and into 3 by 4. So it becomes as q omega mu naught 8 pi r into 1. I guess I have left 1 3 over here. Yes, I have left some 3. Let me check. Cos theta, 3 sin theta minus 4 sin cube theta, and uh, sin cube theta here. This is correct. So I replaced it over here. This is all correct. Integration is also correct. Sin theta is minus cos, no, I guess. Yeah, the integration of sin theta is minus cos. So this will become plus. So as soon as I'll take uh, it will become here 9 if I'll take 3 by 4 common, na? Yeah, and one negative sign will also be there. So I'll just take negative sign common, and then simply we can plug in the values and we'll get the same thing. So 9 to the 18, sorry, 9 to the 18 plus 2, and with one negative sign here, 9 to the 18 plus 2 16. So we'll get 4 and we'll get 3, and with this negative sign we'll get this cancelled. So it is 4 by 3. So we get mu naught omega q upon 8 pi r into 4 by 3. So this is the magnetic field that is at the center of a spherical shell. So I hope you understood the concept, you understood the calculation, you understood the integration. So that's all for this video. See you in next video. Bye bye. Thank you.